Okay, so the last 2 weeks we've done 2 weeks ago limits and last week co-limits. I apologize that the notes are still not up from last week. I mean, as you saw in the lecture, they were from many different sources, and I still haven't managed to compile them all together. Hopefully you had your own notes from last week, but I do intend to put notes from last week up. In contrast, the notes for this week, well, they're not online yet, but they are already written and nicely prepared in one place. What we're going to do is build on some structure that you can derive from products that we saw 2 weeks ago and co-products that we saw 1 week ago. And we're going to generalize those to a rather ubiquitous and important structure. Ubiquitous means occurs in many places. Well, essentially occurs everywhere. Ubiquitous means, so it's a kind of important structure that generalizes both products and co-products. So let's approach it by looking at products with fresh eyes, so to speak. And what I'm going to focus on are the salient properties of products, the important properties of products that are the ones that we include, that form the core of our generalization. So 2 weeks ago, we did general products in categories, but in particular, we saw that finite products can be given. So in general, you have finite products in a category. If you have binary products, you have a binary product, which we tend to write like this, and a terminal object. And the point is that the operation of taking objects x and y and forming the object x times y, we can think of as a kind of multiplication operation on a category. And the one is the unit, the identity of this multiplication operation, the terminal object. So normally a multiplication operation on a set, so one has lots of algebraic structures that involve multiplication operations. You typically have a set together with a binary operation on it, which is your multiplication, and it satisfies some properties. For example, it might be a group or something. Those might be the properties that it satisfies. So to have an analog of a multiplication operation on a category, rather than a binary function on the category, we ask for a binary functor on the category, or a bifunctor as it's called, or a two-argument functor. So I'm going to begin by, we observe that the binary product is a functor. So the times of this is a times operation, not an x. On the category C with products, is a functor from category C, square of the category C, to itself. So the point is that it's a functor in two arguments. So to see this, it's very easy. Sorry, that's not quite what I want to do. So to see this, what we want to do is see that the object action mapping x and y to x times y extends to a morphism action that maps a pair of morphisms F and G from x to x prime and y to y prime, to a morphism from x times y to x prime times y prime. And it's clear if you have any examples of categories like sets in mind with the product, so the set of pairs of the two sets, it's clear what action we have in mind here. We've got a function f on the x sets and a function g on the y sets. Then the function we want here is the function that maps the x component to f of x and the y component to g of y. And that can be defined purely using the category theoretic structure of product, and it's very simple. So the map down here, well, remember, by the universal property of a product, any map into a product, into a binary product, is just a pair of maps into the two factors. And the first map here, well, we need a map from x times y to x prime. Well, we want that to only depend on the first component. So the first map here is going to be f composed with the projection down to the first component. The second map is G composed with projection down to the second component. Okay. So we have a binary product gives a two-argument functor on the category. And because this is a very important functorial structure, in the category with products, we write f product G for that operation on morphisms. And one can verify that this is indeed a functor. I won't do that. But moreover, it's more than just having something like a multiplication operation is more than just having a binary operation. You tend to want some properties to be satisfied. And what's satisfied here, so like ordinary multiplication operations, this operation is essentially associative. It's symmetric, it's commutative, and as I've already said, the terminal object is the identity element for this operation. And I'm going to state in what sense that holds in a category, but it's a little bit more subtle now than a binary multiplication operations on sets, because if you think about it, even in the category of sets, if we think of taking an iterated product like x times y times z, I want to say the product operation is associative, but it's simply not true that this equals x times y times z bracketed the other way, because here we've got a set of pairs of which the first element is an element of x, and here and the second element is itself a set of pairs. Sorry, is itself a pair, and here we've got pairs, but the first element now is a pair. But I guess you can all pretty much see what the appropriate thing is. There is, of course, an isomorphism between these sets, and moreover, it's not an arbitrary one, it's a canonical isomorphism, and it being canonical, it's going to be a natural isomorphism. I'm going to put the indices x, y, and z here, but obviously this is simply the operation that takes a pair of the form. So in set theory, it will take a pair of the form x, y, z, like this. So that's how the triple is there. And it's simply going to rearrange it to x, y, z. So that's how it would work in set theory. But in a general category, we can define, so that's the intuition for it. In a general category, we can define, so alpha is going to be, we want to give a map again into a product, so that's a pair of maps, where the first component is itself a map into a product, so that's again a pair of maps. And the map into the first component here is going to be a pair of maps where we want to get the x component out, so that's the first projection here. The second component in this pair is the y, so that's the first projection of the second projection. Sorry, that's a 1. So here we have the second component, which is the first projection of the second projection. So we get that the composite. And here, the third component is the second projection of the second projection. Okay. So this part here, this is the intuition. In the same way that one is an identity object for the operation, but again, it's not the case that x times 1 equals x, because x times 1 is the set of pairs whose second component comes from the one element from the singleton set that we've chosen as our terminal object. So again, we have maps. So this is an isomorphism. We have maps. And I always forget which way around one uses Greek letters for these. So this one's lambda and this one's rho. And here it's simply that rho is the first projection, and here it's simply that lambda is the second projection. The point is, because we're product, so we would have that for any product set here, but because one is the terminal object, this projection map is actually an isomorphism. So once again, so when a map's an isomorphism, and keep on messing with pens around today. So there we go. Right. So I write this little isomorphism sign down here. So this says we have a binary operation that's associative in the appropriate sense for a category. It's the one object is the identity object for that operation in an appropriate sense for a category. And as I've already said, product is essentially commutative. That is, it has a symmetry property. And again, that's because we have natural isomorphisms, which here we call sigma x. Sorry, I should call that rho sub x and lambda sub x. So these are called sigma x and y, which swap x and y. And in this case, this can be defined. So we want to define a map into y times x. So the first map is the second projection, and the second map is the first projection. So here, sigma xy is I2, I1. Okay. And this data altogether says that binary products, finite products form a kind of multiplication operation on a category. So all these maps here are isomorphisms. They're all natural, and what that means is they're natural in all their arguments. Or another way of saying that is, so let me just briefly, oh, sorry, I should move the camera. So in the case of the associativity operations, naturality says, so I'm only going to write it out in this case, this is the most complicated one, so e.g. for alpha x, y, z, naturality says.
Professor,
yes,
the camera is out of focus.
Oh, it's gone out of focus, right, thank you. Yeah, doesn't like that word. So it says for any maps f from x to x prime, g from y to y prime, and h from z to z prime, the diagram that we get by we do alpha x, y, z to x times y times z, x prime times y prime, z prime here, alpha of x prime, y prime, and z prime, x times y prime, so all primes here, times z prime. Here we have so we have that times d times h bracketed like that, and here we have f times g times h bracketed like that. Okay, so I'm basically just repeating naturality for you, but I did this explicitly because I want to make a point about it. So here, it's a natural transformation between two functors from c times c times c to c. So here we've got the x argument, the y argument, the z argument, and we've got two different functors like that. And the other, so this functor and this functor, and sorry, this functor and this functor, and the natural transformation is between those. And here I'm writing out the naturality diagram in which we consider, which is the correct naturality diagram for this, in which we consider all the morphisms f, g, and h correctly. But a very useful and important fact in category theory is to check naturality in many variables. You can check them in each variable separately. So naturality in several variables is the same thing as naturality in each variable separately. So rather than this single diagram here, we could write three different diagrams, one for f, one for g, and one for h, and make the other morphisms the identities. And sometimes that's, I mean, there are more diagrams, but sometimes it's useful to do that because your diagrams get simpler. Okay. Anyway, naturality in this case means this, and it's kind of obvious if we use our intuition about products that these maps here, these associativity maps, satisfy this naturality property because they're just rearranging components, as it were, and the maps, the maps which are the application of the functor are preserving components and applying each function individually, separately to the individual components. So hopefully it should be obvious that these are natural. Now, what's also important is that this data here satisfies some additional properties. These maps behave nicely with respect to each other. Now, I could write those down in the case of products, but I think now is an appropriate point to go general and introduce you to the general notion of a nice, well-behaved multiplication operation on a category. So I'm going to rub this part off. And such a thing is called a monoidal structure on a category. The idea is we're endowing the category with a kind of multiplication operation which has a neutral element, an identity element, the terminal object in the case of products, and is associative in this sense. So just like a set with a binary operation that's associative and has a neutral element, that's a monoid. That's the algebraic structure for that. A category with the analogous algebraic structure for categories, which is what we're now going to define, is called a monoidal category, or a category with monoidal structure. So this is going to be generalized product. So monoidal structure on the category C is given by a multiplication operation on the category, so that's a functor, and We're not going to call it times because we don't want to prejudice it to look like a product. It's much more general than product. So one typically uses a sort of tensor notation for this. So we've got binary functor. Well, I could write c squared, but on c. And this binary functor should have an identity element. So that's an object belonging to C. And we want it to be associative. We want the object I to have an, and we want the object I to have an, we want I to be an identity element. So it comes together with natural isomorphisms. Here I mean natural in all the arguments that they have. So the first one is the associativity one. So the reason for using the Greek letter alpha is because the alpha is the first letter, like A for associativity. So here we've got alpha x, y, z. So it simply changes the order of the bracketing. But the point is, it's an isomorphism. So we're replacing the equality that we usually have for associativity with being naturally isomorphic. And we want the two for the identity property. So I is supposed to be the identity element for the multiplication. Thank you. So this one's rho. That's another natural isomorphism, and another one, and the other one is lambda. Okay. So here I've said associative and that one's the neutral element, I is the neutral element. I haven't said commutativity yet. And I'm going to leave that as a separate property. So just like with monoids and with groups as well, the basic axioms are about associativity, and then commutativity is an additional property that one might put on top. So the basic axioms are going to be about associativity. So this is the structure we've identified, but it's required to satisfy some axioms that say that it behaves nicely. So the functor and the associativity isomorphism behave nicely in a way. So let's start with the most complicated of the axioms, and to do that, what we look at is what happens if we considered a chain of tensors like this, with everything shifted to the right. And the point is we're going to shift everything to the left, but we're going to associate to the left, but there are actually two different ways of getting there, and we want those two different ways to coincide. So one way is just to apply alpha to this, so that will take the y over to the x. And then if we apply alpha again, then that's right, then we get I think I'm going to be frustrated by this amount of space, actually. So sorry. I'll try to write a little bit smaller and so alpha takes us to x. I've bracketed this the wrong way, haven't I? So, I had a 50% chance of getting it right. And actually, if I thought about it, I would have had a 100% chance of getting it right. But my arms disconnected from my head, And, so it's quite fun to just work these out for yourself. There's basically only one thing you can do. So here we apply alpha again. At least I hope there is. I mean, I'm going to do the one thing that it seems that, that should be Z and W. So I normally like lecturing on the blackboard, but sometimes one thinks that it would be useful to have slides. And when writing out a big diagram, or of course I could have it prepared on the computer, but I'm using the computer for something else. Anyway, this is one way of going there. But another thing we can do is, at this point, use the tensor functor with the identity on X and do the associativity thing in here. So here we do one tensor alpha, we get X tensor. So Y tensor Z, tensor W. And now, if we apply the associativity at this point, that will take us all the way over to something here. So this will, here we'll get X tensor Y tensor Z tensor W. And you see, we're not quite there yet, but just another associativity in here is going to, so here we have alpha tensor 1, the identity on W. Okay. So it's nothing deep in it really, but it's a little bit complicated how one formulates it, but it's essentially, as I say, it's more or less the only thing you can do. And the other two properties are much easier. So the other two properties are, let me just remind myself. Ah, yes. But if we consider an iterated tensor like this, with the identity object in the middle, then we can get this to X tensor Y by taking the identity on X and tensoring that with the, sorry? With a lambda map. Or we can do the associativity and get the identity object next to the X. So there should be a Y. And do rho on the left and tensor that with, and tensor that. So I'm saying tensor because we've got a sort of tensor, a tensor symbol here. Tensor that with the identity. And once again, these two ways of getting rid of the identity object should be the same. And lastly, if we consider I tensor I to I, then both rho and lambda will fit in here. And we want those to be the same maps. So rho of I equals lambda of I. Okay. And those are all the axioms. And essentially, what these axioms tell you is that it doesn't matter how you bracket an iterated tensor product. You know, you can bracket it this way or one of these intervening ways. They're all the same. They're all naturally isomorphic. But they're so naturally isomorphic. These equations here, suffice to say, they're naturally isomorphic in exactly one way. Any two different ways you have of trying to exhibit an isomorphism, they're always going to end up to be the same. There's actually a mathematical statement of that. I'm not going to go into it, but it's called Maclane's coherence theorem for for monoidal categories. So a C with this, a category C with this structure is called a monoidal category. So C with this structure
last two diagrams follow as results from alpha being natural isomorphism.
Sorry, which diagrams?
The last two, the pentagon and the triangle, but those are provable from the three properties we stated, or are there additional specifications?
Oh, no, sorry. This is not, this is, with this structure satisfying these axioms in the monoidal category. The temporal flow is more important than the spatial flow. Yeah, right. So this came after that, and this is just where there was space on the board. So we're going from here to here, and then back to there. Thank you. Right, so that's a monoidal structure. So maybe I want to do examples. We've already done one, which is product, but that's a boring example. But actually, while we're doing the abstract part, let's just finish the abstract part. So I haven't dealt with the symmetry. So let's move the camera. The monoidal structure is symmetric, or sorry, it's not really a property, it's additional structure. So symmetric monoidal structure is the previous, is monoidal structure, is the previous together with, so let's just say plus. So in addition, we require one more natural isomorphism, which is of course going to be like the commutativity of the multiplication operation. There's a swap operation plus a natural isomorphism called sigma for symmetry. So this goes from X, so it's a family isomorphism, natural in X and Y. Okay. Sorry, don't need to put it up there as well. So it simply swaps X and Y. And once again, this needs to satisfy some properties, now saying that it behaves well with respect to the associativity and the lambda and the rho, and so on. So there are three properties here. Well, the first one is the crucial symmetry property, which is if we swap something and swap it back, then that's the same as the identity. We get back to what we started with. So that's very natural. So if we start with x tensor y, we swap it once, we get y tensor x. We swap it again, we get x tensor y. And that's the same thing as the identity. The next one is more interesting. I want x, y, z. And what I want to do is pull z over to the left-hand side. And again, there are going to be two ways of doing it. Either we can just apply the symmetry directly. So then we get z times x tensor y. Oh, I'm using too much space again. Or what we can do is we can apply the associate. Sorry, have I got it the wrong way around again? Right, before you write this down, let me actually write it from my notes rather than, that's the safer thing. Right. Right, we are going to get Z to the left-hand side. So we're going to do, but let's start it with it bracketed in the right way. So Y tensor Z. So one way of getting Z to the left-hand side is to apply associativity to get Z on its own. Have a suitable amount of space. And then apply the symmetry map, sigma, and then we get Z tensor X tensor Y. The other way of getting Z on the left-hand side is to apply this. So here we've done it in one swap, but the other way is to do it in two swaps, to swap it with Y and then to swap it with X. So here we apply identity times sigma on Y and Z, and that gives us X tensor Z tensor Y. Then we want to swap the Z with the X, but in order to do that, we need to use the associativity map to get the Z next to the X. And then we can apply sigma on the left here, the swap on the left. So here we have sigma times the identity on Y. Now we get Z tensor X tensor Y. But we've not quite got the same thing because they're bracketed differently. So again, we use the associativity map to take us from the top right to the bottom. And the last thing is that our row and lambda maps are the same thing modulo the symmetry. So if we start off with X tensor I, we apply the symmetry to it, we get I tensor X. Then the two ways we've got of getting into X are the same thing. So here we're going down, thank you. There we're going down row, and there we're going down lambda. And a category with all this structure is called a symmetric monoidal category. C with the above structure is a symmetric monoidal category. When you say a symmetric monoidal category, the structure, the multiplication operation, and these maps between them, these are not uniquely determined by the category. The category may have several different symmetric monoidal structures or monoidal structures on it. So when you say a symmetric monoidal category, you mean the category C together with a particular choice of this data. Just like a group is a set together with a particular choice of a multiplication operation and an identity element on it. Okay, so let's look at a few examples. I'm going to save the most interesting examples till after the break. So examples, category C with finite products, that was what we started with, so we've already seen that data. So this is symmetric monoidal category. Okay, so that was our starting example, just to note it down. There is an example of very similar generality that's not products. Can anyone guess what I'm talking about? Sums, so coproducts. So in fact, the axioms for a monoidal category are self-dual. in the sense that if you've got monoidal structure on a category, the same structure gives monoidal structure on the opposite category. We use the same functors, and for the morphisms, you simply use the inverses of the morphisms you had in the original category. Because everything's an isomorphism, it's the inverses, you know, things work also in the opposite category. And so if finite products are monoidal structure on the opposite category, that means finite coproducts are monoidal structure on the category itself. And it's just like with groups, you know, groups tend to be, we have multiplicative groups and additive groups. We're generalizing this sort of general notion of associative operation. It's natural that we have additive ones and multiplicative ones. So these are the multiplicative ones. We also have C with some finite coproducts.
Professor?
Yeah, that's
the camera hasn't turned.
Oh, sorry.
Yeah.
It's again symmetric. Another, just to mention it, another sort of nice class of examples is if C has symmetric or not, has monoidal structure. Then so does the category I'm going to call C sub iso, which I won't write down what this means. This is the category that has the same objects as C, but whose morphisms are only the isomorphisms in C. So like finite set sub iso would be the category whose objects are finite sets and whose morphisms are bijections between finite sets. And this category actually is quite important in combinatorics. So it's quite often useful to restrict to a category whose morphisms are isomorphisms. Such categories are called groupoids. So remember, a group is a category with one object, all of whose morphisms are isomorphisms. The groupoid is a category with perhaps many objects, but all of whose morphisms are isomorphisms. So C iso is a groupoid. But the point is, because the monoidal structure only involves isomorphisms, and functors automatically preserve isomorphisms. If you have monoidal structure on a category, you then throw away the non-isomorphisms, you still have monoidal structure on the remaining category. Okay, well, it's exactly 11 o'clock, so we'll have a 15-minute break till 11:15. I shall pause the recording. Okay, so in the break, I rather overzealously cleaned the boards of the examples, and then having done so, realized that I then wanted to extend the list of examples. But never mind, we can remember that we had the examples of finite products, finite coproducts. We can also restrict monoidal structure to the group, the underlying groupoid of a category. Already having the examples of finite products and finite coproducts gives two concrete examples showing that the notion of monoidal structure on a category, or monoidal product, or monoidal tensor, as it's sometimes called, is not determined up to isomorphism. So there may be many really different monoidal structures on the category. I'm going to do two more. Another symmetric one. If we look at the category of rel, so the answer to the week 5 puzzle from 2 weeks ago, that was about what products are in rel. I don't know if anybody worked that out. Products in the category of relations are the same as coproducts in set. And in fact, coproducts in set are also coproducts in the category of relations. So in the category of relations, products and coproducts coincide, rather like in the category of finite dimensional vector spaces, where also products and coproducts coincide. So in rel, we have one symmetric monoidal structure given by products in the category, products in the category, which are co-products of sets, which are also co-products in the category. So those two examples do coincide in REL. But there's another monoidal structure in REL, which is product in set is symmetric monoidal structure, or let's say gives. So I've worked this out in a little bit more detail in the notes. Gives symmetric monoidal structure on REL. So product of two sets doesn't enjoy the universal property of a product or co-product in the category of relations, but nonetheless, it is a symmetric monoidal product structure on the category of relations. So all the examples we've seen so far have been symmetric. A very simple example that's not symmetric is to look at the category that in my notation is CC of endofunctors. So that's the category of all functors from a category C to itself, with natural transformations of the morphism. So endofunctors on C. And in that category, so an object now is an endofunctor on C, and we simply define F tensor G to be the composite of F and G. And I is defined to be, it's related to monads, but let's not, you can ask about that afterwards. I is the identity functor on C. And it's actually really easy to see this as a symmetric monoidal structure, because if you consider F tensor G tensor H for the associativity, well, it's just composite. So actually, however you bracket it, you just get the same equal composite functor, F, G, H. So this is literally the composite functor. And moreover, if you product with the identity functor, well, you're composing with the identity, so you stay the same. So the isomorphisms, the alpha, the associativity, the rho and the lambda are just the identity functions in this case. So this is what's called a strict monoidal category. It's the first example we've seen of a strict monoidal category. So alpha, rho, and lambda are all identities. But it's not symmetric. The composite FG is very different from the composite GF in general. So it's very non-symmetric. Okay. So now I want to spend a bit of time on the main example that I want to give of a category with a monoidal structure that's not of any of the forms we've seen before. It's an example of a whole family of examples that come from mathematics, which are examples provided by constructions in mathematics known as tensor products. So maybe you've met some tensor products in maths, maybe you haven't. Tensor products tend to be examples of monoidal structures of monoidal structure on the categories they're defined on. So I'm going to give one example of this, which is one of the easier examples of tensor product in mathematics, but I'm not sure if it's going to be familiar to everyone. So, I mean, I'm not going to poll the people on Zoom, but the people in this room, how many of you know the tensor product of vector spaces as a mathematical? Okay, very good. So it's almost everyone. And somebody left, but I think temporarily because the paper's there, but anyway. But to work up to it, I want to consider the case of matrices, which is in any case a little bit easier to understand, although the details are in some sense a little bit hard to work write down. So remember the matrices over a field K had objects n, natural numbers, and morphisms from n to m were n by n matrices. And I want to define a tensor product on matrices. Well, on these, we think of the object n as the vector space K to the n. And the linear maps are represented by matrices. So the tensor of two objects, m and n, is simply m times n. And the identity object is simply 1, which is the identity for multiplication. But we want to define the functoriality properties of this. Actually, maybe before saying this, let's give a motivating example that hopefully can be motivating to some of you. So in quantum mechanics, states are vectors in a Hilbert space, where the Hilbert space is a complex Hilbert space, and it's the dimension of the Hilbert space is kind of the number of configurations that you have, possible classical configurations of the system in some sense. Well, it sounds a bit complicated, but in the case of something simple like quantum computation, for those who know something about quantum computation, you have the notion of a qubit, a quantum bit. So a bit has two classical states, 0 and 1. So a qubit is represented as a vector in the Hilbert space, which we're just going to view it as a vector space, complex number squared. Okay, so that's one qubit. But if you've got n qubits has a u after the q, make it a nice English word. So n qubits are represented as a vector in, well, if you've got n qubits, so you've got n bits, so there are 2 to the power of n classical configurations that those bits can be in. So n qubits, a vector are represented as a vector in c to the 2 to the n. And the point is that's kind of, you view that as an n-fold tensor product of the vector spaces C of the vectors, the two-dimensional vector spaces. Or if we're viewing things as vectors, so if we're viewing a vector as a column vector and the linear transformations as matrices, so our original vector had 2 components, and now if we've got n qubits, we're tensoring those 2 times 2 times 2 n times, and so we're multiplying each time, and we get 2 to the power of n. So I realize not everyone knows about quantum computation, probably very few, but just in case for some people it's useful to make this connection, the point is that somehow the tensor product is the right way of creating a new vector space. If you think of the basis as the classical configurations, such that the new space of classical configurations is all possible choices from the first space and the second space independently, so to speak. Otherwise, you can understand the mathematics. So I've just realized I didn't prepare how I was going to say this. I realize it's quite hard to tell the story in these. I mean, quantum computations, quantum theory in general is something that takes a bit of getting one's head around. But there was something else I wanted. Yeah. Sorry?
Were you trying to tell us how the matrix looks?
Well, I do want to say that, so let's do that. So here we want to say how to tensor two matrices, and hopefully this is something you've all seen in linear algebra. So if you're given a matrix, so it's an m by n matrix considered as a morphism from m to m, and an m prime times n prime matrix considered as a morphism from n prime to m prime, then the morphism from n tensor n prime to the A tensor B map to n tensor n prime is the matrix. So we want to give a matrix with m times n prime rows and n times n prime columns. And hopefully you've seen this construction before. So B is an m prime times n prime matrix. So we can fill this matrix with m copies of B vertically and n copies of B horizontally. So that's, yeah, so the m prime rows of B, we're considering m copies of that. So we've got m times n prime rows, and here we've got n times n prime columns. And we multiply each matrix by the appropriate entry from A. So here we have A11. I'll use little a's for the entries. M1, right? So is that yeah, no, A1. AM1, yeah. A1N, and I hope you've seen this kind of construction in linear algebra before. The point is it's a tensor product. So in the notes I've written out the symmetry map and the lambda and the rho. It's actually to write out the associativity map precisely. It's not complicated, it's just a matter of rearranging things, but working out exactly what goes where is quite a good exercise. So, but anyway, let me just leave you as an exercise. So work out alpha, lambda, rho, and the symmetry. That's matrices, and that's kind of a special case of the tensor product on vector spaces, which is an example of, which is a very canonical in the sense of as a very what's the right word? A very typical. I was looking for a different word, but it means pretty much the same thing. A very typical example of a paradigmatic example of the category with monoidal structure. So if you know, as most of you do, the tensor product on vector spaces, you'll know the construction of it is a little bit complicated. But the idea behind it is not complicated. So the idea behind it is the tensor product B tensor W of two vector spaces enjoys the following property. That you can code up bilinear maps in V and W as linear maps out of the tensor product. That's the key idea to it. So it enjoys the property for any bilinear, and let me carry on. For any bilinear map out of B and W. So remember, a bilinear map into some other vector space is a function in 2 arguments so that it's linear in each argument separately. So for any bilinear map, there exists a unique, this is bilinear, there exists a unique linear map, let's call it G, out of the tensor product, that essentially represents the bilinear map. So such that, so we've got P times W, the tensor product B tensor W. Here we've got the G map goes to U. Here we've got F, the bilinear map. And the point is there's a particular bilinear function here from V and W into the tensor product, which is kind of, in the sense, the universal bilinear function. In this sense, that any bilinear function from V and W is a linear function composed with that universal bilinear function. So we should put at the start, there exists bilinear psi UV of psi VW goes from B times W to B tensor W, such that for any bilinear map, this diagram commutes. So a question for you, in what category is this diagram? Sorry? It's not in the category of vector spaces. This diagram here, why not? Well, no, so we've assumed, so I'm saying for any U and for any, so U is a space, so U is a vector space. Let me be, so only the map G is in the category of vector spaces. Can anyone see why? So the point is that a bilinear map is a function. It's not a linear function. So we do have a product space, but a bilinear function is not linear. So this, yeah, we do have a product vector space, but this is not, the psi and F are not maps in the category of vector spaces. So this is a diagram in the category of sets. Okay. So it's a bit subtle, but nonetheless, this property alone, one can define the vector space, the tensor product in many ways. I mean, the standard way is to take all pairs of vectors as a basis for this vector space, and then, but then you need to quotient it by some equivalence relation. It's all a bit messy, but this characterizing definition defines the tensor product up to linear isomorphism. So this completely characterizes the tensor product. And the point is, this tensor product is endows. So this is, we can put it at the bottom here. So this is symmetric monoidal, or gives would be a better word to say, symmetric monoidal structure. On the category of vector spaces. Okay, but it's something very different from, it's not like a Cartesian product or a co-product or something. So of course you need to find alpha, lambda, rho, the sigma symmetry for this. So I'll let you do that. If you've worked with yourselves, if you've worked with tensor products, you should be able to do it. Everything can be done though abstractly from this characterization. So you should be able to prove that this is a symmetric monoidal structure without ever using an explicit construction of the tensor product space, an explicit definition, just the fact that it satisfies this characterization. Right, so that's monoidal structure. I'm now going to start something that will continue next week, which is to look at something very useful one can ask for on top of monoidal structure. So the monoidal structure provides a kind of product on the category. When you have a product operation often determines a kind of exponentiation operation. So like an iterated product. We're going to see now, we've got a monoidal structure, there's a natural notion of having an exponentiation operation associated with the product structure. And in the case of, so maybe I'll start with the case of, since we're here, it's not the easiest case, but I'm going to start with the case of vector spaces, since we're actually just dealing with them now. So what would be an appropriate notion of exponential here? Well, the idea is an exponential, so like in set theory, we often write x to the y to mean the set of functions from y to x. So the appropriate notion of exponential here is like a set of functions. So for vector spaces, we're given v and w, then I'm going to write v arrows w with a lollipop. Not good notation, but anyway, for the vector space so v arrow w is the set of linear functions from v to w. So we've already basically considered this in an earlier lecture. So it's easy to see that linear functions form a vector space. There's a zero function. You can add two linear functions and you can scale and multiply them. We've already worked with a special case of this, which is the dual space. So the dual space can be defined as the lollipop. So this is called lollipop because, you know, lollipop that children lick. There's a lot of lollipop lying on its side. So the dual space can be defined as V lollipop K. And the point is we're going to characterize this space in terms of the tensor product as an exponential associated with the tensor product. I haven't said in general what that means, but we can see in this example, I can tell you the data that we're looking for. So let's consider, so one thing we have associated with a function space is there's an obvious function, evaluation function, we'll call it, which takes a linear function f and a vector v onto the application of f to v. So that's a function that takes us from our space of linear functions together with a vector in the space v, applies the function to the vector and gives us back a vector in the space w. Now, this function is not linear. But it is bilinear. That's very important. So if we fix v, then this function preserves addition of functions f and scalar multiplication of functions f, just by how it's defined. I mean, and similarly, if you fix f, it preserves addition in scalar multiplication in v. So this is bilinear. So by our characterization of tensor product, it corresponds uniquely. So it corresponds uniquely to a function out of the tensor product. So we have a function which we're going to call the evaluation function, or the evaluation map. From the space of linear functions, the evaluation function takes us to W. Okay. Right, is there anything not clear about that while I'm clearing the board? So the function itself is defined on pairs, one from the lollipop space of linear functions, the other from the underlying vector space V. But to view that evaluation function, so that's the evaluation function that simply evaluates the function on its argument. And to view that function as a map in the category of vector spaces, we need to make it linear. And we make it, and because it's a bilinear function, we make it linear by considering it as a function out of the tensor product. Okay. And then we notice that this satisfies the following property, which is given any function, any linear function, well, let's do it like this. I'm departing from my notes because I've decided to try and write it like this. Given any bilinear function f from u times v to w.
Sorry for the interruption.
Yes, I've not moved the board. Is that the problem?
Yes.
Yes,
Thank you.
Not the board. I'm not moving the board. I'm moving the camera. But we can apply the principle of relativity. So which might explain why I'm feeling dizzy. So given any bilinear function, there exists a unique linear function lambda f from u, so it's a linear function from u to b lollipop w. Well, actually, I'm going to say there exists a canonical linear function, viz. So that means, namely, a function, so lambda f applied to a vector from u is simply the function that takes a vector from v and maps it to f u v. Okay, we're given a bilinear function, and the fact that this function is linear essentially says the same thing. So you could do this. You could define this for any function f whatsoever, but the linearity of this essentially says the same thing as the bilinearity of f. It's the same content. This function is linear precisely because f is bilinear. And the point is we can code this construction up using tensor products. So what happens is that for any So in other words, using the fact that bilinear functions correspond to linear maps out of a tensor product, so another way of writing that is for any linear map from U tensor B to W. So we're now looking, so I want to reformulate this using just the category maps in the category of vector spaces, so namely just linear maps. So for any linear function, there exists a unique linear function lambda f, which goes from U to the lollipop space, function space, such that, well, we want to say there's a unique function. Basically, there is a unique such map that forces lambda f to be this function here. And we can write that up in category theoretic terms as follows, that if we use our evaluation map, sorry, so F on the evaluation map. The point is we start off with an F here, which we think of as a bilinear function. We can convert that bilinear function into a linear function, lambda f, that goes from U to the to this function space, as it were, this exponential, and it basically corresponds to the function that evaluates the arguments of f1 at a time. So we take the first argument of f and map it to a function that takes the second argument of f and then evaluates it. Okay. So that's how things. And this basically characterizes, this property characterizes this lollipop space in vector spaces. So I don't know, it would have helped to give the general definition before. But I now want to give the general category theoretic definition, and then right, so the general category theoretic definition is a category with monoidal structure. I just need to move the camera. Is what's called left closed if for every pair of objects xy, there exists an object which I'll write like this, which we think of an object, just like a product object we think of as a product set or something, we think of this as an object of functions from x to y. So, and an evaluation map. So evaluation is just a name here, map, that goes from x, y. So the point is we think of this as taking a function together with an argument and evaluating the function by applying it to its argument. So that's going to give us an object of y, such that for every map from some object z tensor x f to y. Let's continue over here. There exists a unique map from z to what we'll call lambda f, which goes to the functions, such that the diagram below commutes. So we have the same diagram we had before. F takes us, F is our given function, but the function, we think of it as a function of two arguments that gives us back something in y. And we can get that function of two arguments by firstly taking a z and using and taking an element of z and using it to get what the function does for that fixed value of z. We get f as a function of x, so that gives us here we have the evaluation, right? So
If something is wrong, there's supposed to be a Z somewhere.
no, there's not supposed to be a z in the top left corner.
Sorry.
Yeah. So given a 2-argument function from z and x to y, we have a unique way of getting it as a 1-argument function in z that gives us back the 1-argument function that's the function in x once we fix the z given by f. And this corresponds to something very familiar in set theory, which is in category of sets. If we look at if we look in the category of sets and we interpret the tensor product as the product of sets, then we really are looking at 2-argument functions, and this is basically implementing the well-known bijection between, so in the category of sets. Well, whenever we have this gives us the bijection between morphisms in 2 arguments and morphisms in 1 argument of this form. Okay, we always. So often, so sometimes one writes this to mean they're in one-to-one correspondence. So this is saying maps of this form are in one-to-one correspondence with this. We look at the category of sets. We interpret this as product, this as function space. This is a very familiar fact that the 2-argument functions from z times x to y are the same thing as functions from z to function space x to y. And this plays a key role in functional programming. This is one of these directions is known as currying and the other one is known as uncurrying. But actually at the moment, I don't remember which one is which. So maybe somebody can remind me about that. So here, let's repeat the spatial flow that we had before. Yeah, so we've defined the notion of left closed monoidal category. There's a right closed notion in which you basically reverse the order of this evaluation map and everything else, adjust everything else appropriately. But the difference is only important in the case that the monoidal structure is not symmetric. And since we're only going to ever consider this in the case of symmetric monoidal structure, we won't need left closed versus right closed. So in the case of symmetric monoidal structure, we simply say closed. So a closed monoidal category. But a very important special case here is the case in which the monoidal structure is a product, not symmetric monoidal structure, but an actual product with its universal property. And this leads to a very important kind of category called a Cartesian closed category. So a Cartesian closed category is a category with finite products that is closed in the previous sense, where we take the finite product as the monoidal structure. So with respect to the monoidal structure, given by finite products. And I think from the definition, I've already essentially talked you through the reason that the category of sets is Cartesian closed. One simply interprets x arrow y, sorry, the brackets x, y as the set of all functions from x to y. So set is Cartesian closed. And it's very easy to see it satisfies that defining property. So it's the set of all functions x to y. And the evaluation map is the expected evaluation map. Take a function, take an argument, and apply the function to the argument. So I won't even write that down. Right, we didn't have a week 6 puzzle, so I'm going to give a week 7 puzzle. So in the week 3 puzzle, we looked at 2 functor categories, like the functor category from a group to set, and the functor category from what I, for no good reason, called capital lambda to set. So hopefully by now, some of you have worked out that the category G sets is the category whose objects are left G actions and whose morphisms are what are called equivariant functions between left G actions. So there's a category of group actions. And the category, so this functor category is isomorphic to the category of group actions. This functor category is equivalent to the category of graphs that we had in a couple of lectures ago when we were defining diagrams, or graphs or quivers. So this is isomorphic to left G actions, and this one is equivalent to quivers or graphs and graph morphisms. So the puzzle is, for this one, both these categories are Cartesian closed. I'm telling you that. The question is, calculate the exponential structure explicitly. So work out the structure explicitly. So by exponential structure, I mean this bracket object. It's like an exponential object in the category of in the category. And we'll justify that a bit more later in the course. Right, okay, well, it's exactly 1 o'clock. So sorry, not 1 o'clock, 12 o'clock. It's 1 o'clock in South Africa where some people are, no, hang on. I'm not sure which way around it is. Anyway, it doesn't matter. It's time for the lecture to finish. That's the important thing. So I'm going to stop the recording.